Hi, my name's Jessica Carrera. This is Gilson Texera and Joanza Foster and Annalise Sanchez, and we're going to present the Audubon Land Surveying System project. Our advisor was Dr. Paul Gendron. So just an intro, the Audubon Society of Rhode Island protects wildlife and their habitats through conservation, education, and advocacy to benefit people and all living things. They're currently seeking accreditation by the Land Trust Alliance. However, to do this, they have to be able to monitor their land once per year. This is very hard to do because they have over 100 parcels, and some of their land is surrounded by like 4 houses, and they can't get to it without encroaching on people's property. They need to monitor the parcels of land for health and status of vegetation, encroachment on the property by neighbors, and evidence of dumping, cutting, or other destructive activities. So now I'm going to turn it over to Annalise.
The following is an overview of our presentation today. We have our system requirements, functional design, design concept, technical design, test plan and test results, planning and project management, conclusion, and we'll have a demonstration at the end. System requirements, which are generally defined at multiple levels from highest to lowest, and these were established to ensure a common understanding between the Audubon Society and the engineering design team. They include customer requirements, engineering requirements, and constraints, and standards. So for today, these are our customer requirements, and we have 11, so today we'll just go over our top 4, and they're highlighted in yellow for reference. Number 1 is that the drone should have the means of capturing images or video footage for each parcel of land. Number 4, the drone should be able to be controlled from the nearest street. 5, resolution of the image should allow to see trees, evidence of dumping, cutting, and heating into each parcel of land. And number 8, the final image of the parcel of land should be in a JPEG format of the following name, parcel name _ date. Engineering requirements, which are derived from customer requirements, again are referenced in yellow. Our first one has a sub-requirement, and it's that the drone needs to be equipped with a camera, and if it does not, it needs to have a placeholder for a camera. Number 4, the drone should have a connection that works up to the nearest street up to 1 mile, and this was accomplished by purchasing additional antennas. Number 5, the resolution needs to be approximately 2 to 3 feet at 400 feet, worst case scenario. And based on our calculations for the resolution, with our GoPro, this requirement was met. And number 8, the scripting language should allow the customization of the name for the JPEG. And our MATLAB application, which includes a GUI, allows the customer to do this. And then we have our constraints and standards. For constraints, we have the maximum distance that the drone needs to operate from, and the total time it takes the user to fly the drone. And for software, we have it must be compatible with the devices that the Audubon Society has. And for standards, we have the Federal Aviation Administration, or the FAA, which is a guideline for flying drones. And of course, the actual code of ethics.
So for our functional design, we have our software overview and our system diagram. This is our system diagram. We're going to get parcel data from the customer. From that, we're going to get GPS coordinates and use that to program a flight path for the drone. The drone is just going to fly that flight path over the land and take a video of it and store it on an SD card. The SD card is going to be uploaded to the computer. We're going to use MATLAB to process the video and get a complete picture of the land. This is our software overview. We start by asking the user how many end frames they want to process, like every 1 frame or every 2 frames. We then ask the user what type of transformation they want to use, projective, affine, or similarity. And the difference is similarity uses 2 points to match between 2 images, affine uses 3, and projective uses 4. After that, we extract the features from each frame. We'll first ask the user the location of the video, and then extract the features from each frame. We then match the features of that frame to the previous frame and estimate the geometric transformation. And then we warp each image onto the panorama, and from that we get a complete picture, and then we save the image. Next is our design alternatives for the drone and the software that we use. This is our decision matrix for the drone. We have 7 categories: camera, maximum distance to operate, battery life, cost, resolution, storage, and communication link. And they're given a weight between 1 and 7. And we have 5 alternatives for the drone, and they're all ranked 1 to 5. And the way we calculated it was we multiplied the rank that each drone got in that category by the weight, and then summed it up for a total possible of 140 points. And the drone that scored the highest was the DJI Phantom. However, we chose the 3DR Solo. The reason we chose the 3DR Solo, even though it didn't score well in our decision matrix, was because it didn't score well because it did not have a camera. This meaning it scored low in the storage, resolution, and camera portion of the matrix. However, it has a gimbal that you can attach a camera to. This would increase the score of the drone. It also doesn't have good range, but with the new antennas, it would significantly increase the range of the drone, thus increasing the score. It also has a third-party application that lets you fly the drone autonomously and set a flight path for the drone that you can resave and fly at any time. And it also has a feature that when the battery gets too low, the drone automatically returns home. This is our decision matrix for the software. Our categories are execution speed, tools, community support, graphical compatibilities, data analytics, and the learning curve. And our alternatives were Python, Octave, R, and MATLAB. And the program that scored the highest was MATLAB with 67 out of 84 points. And we did choose MATLAB. It was the software that scored the highest. It's also the one we are most familiar with. It also has a image processing and computer vision toolbox that are useful for our application. And we also knew that the MATLAB code can be transformed into an application that can be put onto a different computer that doesn't have MATLAB installed.
So now I'm going to talk to the technical design. This pertains to performance calculations, analysis, simulation, and prototyping as applicable to each of our following subsystems. We have subsystem A, which is our 3DR Solo, and subsystem B, MATLAB. So first of all, I'm going to talk about the resolution calculations. So we had to pick a GoPro that would work with 2 to 3 feet per pixel of resolution. That was our customer's requirement, worst case scenario at 400 feet. So we did the calculation for the Hero 3 Black Edition. This was one of many. And we figured out that at the worst case scenario, at a degree angle field of view of 84 degrees, we'd have a 0.61 feet per pixel, which is much higher than the customer required. So we went with this drone. We typically fly the drone at 350 feet. This gives us the best image that we've seen so far, or video. So now I'm going to talk about tower and solo applications. The tower application is the third-party app that allows the sponsor to plan and save their autonomous missions. You can pick the altitudes and delay of waypoints when you're planning the mission, and you can interact with the GoPro while in the air, so you can stop and pause the video whenever you need to. And then I'm going to talk about the solo application, which is just what comes with 3DR Solo. You use it in conjunction, and you can fly it manually, and it also has a return home feature. We only recommend that the customer uses the manual version of the flying the drone if need be. So this would only be if the drone was going to land on something that wasn't flat. We would ask that they would pause it mid-air and land it themselves, because sometimes we had an incident where the drone flipped over and all the propellers broke off because it didn't realize that it had landed, so it didn't stop. So the gimbal and antenna, we just bought a gimbal to stabilize the camera so that the video was more clear. And then we bought additional antennas so that we could fly the drone a mile away from the user, instead of the half a mile that it was. Okay, we also made a land surveying system user manual. This was because the tower application was pretty hard to figure out at first. We had to watch a lot of YouTube videos, and we didn't want to put the customer through that. So we made our own manual, included hyperlinks to the manuals for the 3DR Solo and the GoPro. As you can see, the first image, you can see that you can take off, disarm, or auto the drone. And then the leftmost picture shows that it's a safety feature, and you slide it if you're to take it off. So you hit takeoff, and then you have to slide it so that you couldn't just hit takeoff and have the drone go while it's in your pocket or something. Okay, so now I'm going to talk about the MATLAB code. So pretty much we process a video frame by frame, finding the transformations and detecting and extracting features of each frame to compare to the next frame to create a panorama image of the parcel of land. So this is just a high-level overview of our code. We ask the user for the number of frames, transformation type, and video location. We read in the video. Then we calculate the number of frames in the video. Then we calculate the number of frames based on what the user entered. We read the frames, detect and extract the features in the first frame, and then we use the previous features to match with the new features every frame that this occurs. Then we're going to continue until all the frames are processed. Then we estimate the geometric transformation based on the matching points, and then we ask the user to name the parcel and where to store it, and they create the panorama. So now I'm going to talk about our GUI, Graphical User Interface. This allows the user to have some say over the image processing process. So we found out that using every other frame was the best option, but we also gave the option to process between 1 and 10 frames. This is because sometimes you could get a good image using less frames and it took less time to process the image. And there's an error message that's present if you enter anything else. And then you can also pick what transformation type you'd like to use. We recommend projective. It gives the best overall view that we've seen. But sometimes you can use the other projections only if, the other transforms, I'm sorry, only if the image comes out really bad. The user also chooses what folder their video comes from. We recommend that you put the parcel in a folder, and then in another folder you're going to have the parcel name and the date, and then you save the video in there so that it's organized, and then save the image back to that parcel and year. So now I'm going to hand it over to G to talk about test plans and test results.
Now we'll talk about test plan and test results. For the test plan, we use a verification cross-reference matrix, which summarizes the verification method of each engineering requirement. And there are 4 verification methods, which are inspection, analysis, demonstration, and test. For the test result, we use a test summary table, which summarizes the result of each engineering requirement, indicating whether or not they pass or fail. For the test plan, we have different engineering requirements, but I will only go over the ones that were mentioned previously. For engineering requirement 1, which it has a sub-requirement 1.1, we use inspection as a verification method. And for engineering requirement 4, we use test as the verification method, and for 5, we use both analysis and test for the verification method. And finally, for number 8, we use inspection as the verification method. For the test results, for test ID number 1, it failed. We tested to see if the drone comes with a built-in camera, but it fails because it does not come with a built-in camera. But it has a subtest, which is 1.1. It passes because the drone has a placeholder that allows the camera to be mounted, and it also supports the weight of the camera. And for test ID number 4, here we're testing to see if the connection between the controller and the drone is operable up to a mile away. And it passes because we purchased additional antennas that allows the drone to be operable from a mile away. And test ID number 5 passes because of the resolution calculation that Jessica just presented. And test ID number 8, here we're testing to see if the user is able to enter a name for the final image, and this is possible because the MATLAB graphical user interface allows the sponsor to insert a name of their choosing. For planning and project I will talk about the planning project management for the fall semester 2017 and spring semester 2018. For the fall semester, as you can see, we use the bar graph. The green bars represents the proposed hours, and the blue represents the actual hours. And as you can see, we underestimated a lot of the tasks, the amount of hours it would actually take to complete a task. And we followed the same scheme for spring semester. Again, we underestimated the number of hours that we actually needed to complete a project.
So in conclusion, we are going to go over our lessons learned in the summary. So in conclusion, we learned that the engineering design proposal may not always correlate directly to what that customer actually needs or wants. So having continuous meetings and discussions with the customer definitely led to a successful project. We also learned how to work as a team, either dividing up the work and coming together at the end or working together on it. And then time management, we had a hard time at the beginning and the end, estimating how long things would take. We ended up underestimating a lot of time it would take to complete a task. So in summary, in the past, the Audubon Society had no means of monitoring land besides on foot. This is really hard when you have buildings surrounding land and you can't get to it without knocking on all the neighbors' doors and asking them if you can go on the land. But using our Audubon land surveying system, we now have a means to survey this land once a year, every year, and they can get accredited by the Land Trust Alliance. So the 3DR Solo, in conjunction with the GoPro, takes video footage above each parcel of the land, and then we use the MATLAB code to process the data and create a panorama image. So now I'm going to show you a little demonstration. We took a video at UMass Dartmouth on April 23rd, and then we're going to show you our final image obtained. So you're going to see here that the drone's going to rotate, and then it's going to fly to the next waypoint. So what it does is it has to orient itself to the next waypoint. We ask that the customer puts in a 5-second delay in the first waypoint and a 5-second delay at the back of the last waypoint, because it's easier to process images when you're, first of all, in the sky and you're not taking into account the drone taking off or landing or any other land that's not necessary. And this is because it's harder to do transformations when things aren't at the same height and things look different, and you get really bad results because we tried it like that. So now I'm going to show you our final image. We use the projective mode, which we recommend, and we process every 2 frames. So this is our final image obtained of the land. The resolution is really good, and if you zoom in, not on this one because it's actually a picture of a picture, but if you zoom in, you get really high quality and you can see what's between the trees and everything. So they'll be able to see if anybody's on their property. So I just want to thank our sponsors, Don Heitzman and Terry Meyer, from the Audubon Society, and our professors, Dr. Paul Gendron and Dr. Vance McCullen, and of course, Fernanda Patello and the whole ECE department. Any questions?